Okay, in this lesson we're going to look at the identification of unknowns. We're going to recap the tests for unknown gases and then move on to the 5 different tests for unknown ions that you need to know for this part of the course. So there are 4 different gases you need to know the tests for and the results, and that is hydrogen, oxygen, carbon dioxide and chlorine, and they are all from the combined science spec. And then for the triple, you also need to know the 5 different ions tests. We have the flame test for metal cations, we have the precipitate test for metal cations, we have the halide anion test, the carbonate anion test, and the sulfate anion test. So you will have a copy of this worksheet for you to be filling in as you're watching this video, which will allow you to basically just have a summary sheet of all the different tests, all the different methods, all the different results, all on one sheet. And you can use this to help you answer the exam questions that are going to be sent to you after this lesson. And also, if you can just learn everything on this sheet, then you're going to put yourself in a really good position. So we'll start with the gas tests. So for the hydrogen gas test, the most common answer people give is squeaky pop test. But if you're being asked to describe the test, just saying squeaky pop test does not describe the test. So the mentality you should have for all of these is you're going to describe the actual physical test and the result. So the actual test for hydrogen gas is to add a lit splint and it burns with a squeaky pop. Okay, so the test and the result. And the reason it does that is because the hydrogen ignites and it combusts with the oxygen in the atmosphere, it produces water vapor, and that little squeaky pop you're hearing is actually a mini explosion in the test tube. The oxygen gas test, you would collect the gas and you would add a glowing splint. So that is a splint that was lit, but you've blown it out and now it's just got a glowing ember on the end, and you place that glowing splint into the gas that you think is oxygen, and if it is oxygen, it will reignite the splint. And the reason for that is because the splint was originally burning, it was a fuel, but when you've blown it out, when you put it into the test tube where there's more oxygen, it's able to reignite, because if you increase the amount of oxygen, then the combustion is able to continue. Carbon dioxide. Now you could have a lit splint and place that in carbon dioxide and it would extinguish, but that doesn't necessarily tell you it's carbon dioxide, because if you did that same thing with sulfur dioxide or ammonia, it would also extinguish. So the test for carbon dioxide gas is to bubble it through lime water and it turns cloudy. So the test is to bubble it through lime water, the result is it turns cloudy. And that's because lime water is calcium hydroxide, and when you bubble carbon dioxide through it, it forms calcium carbonate, which is insoluble. So that cloudiness that you're seeing is actually solid calcium carbonate being produced. If you left it long enough, all of that calcium carbonate would sort of settle at the bottom, and you would actually have solid calcium carbonate at the bottom of the test tube. The chlorine gas test, you add damp litmus paper. It's really important that it's damp, and it will initially turn red and then bleach white. And this second bit, this bleaching white, is really important because that's what's unique to chlorine. If I did this test with sulfur dioxide, it would turn red, or nitrogen oxides, it would turn red, because that just tells you it's an acidic gas. But the fact that it bleaches white, that's what identifies it as being chlorine. And that's because of this reaction. The chlorine in the atmosphere, the chlorine that you are adding to your litmus is going to react with the water on your litmus paper because it's damp. That's why it needs to be damp. And the chlorine reacts with the water and it forms HCl, which we should recognize as hydrochloric acid. That's why it turns red. And it also produces hydrogen chlorate. And this ClO here, the chlorate ion, that is the bleaching ion. That is the ion that's responsible for bleach. So if it wasn't damp, none of this would happen. And the reason it goes red is because of the HCl being produced, and then it bleaches white because of the hydrogen chlorate, the HClO, being produced. So moving on to the triple content, then you need to be able to identify the ions present in a compound. Now, we're talking about ionic compounds here, so we're going to be talking about a positive ion and a negative ion. So you need to be able to identify the positive cations and the negative anions. So you only need to know the tests for the metal cations. So the first one is the flame test, and it's quite a simple test. You take a wire loop and you dip it into some hydrochloric acid and then place it in a Bunsen flame, and that is just to remove any contamination from the wire loop. Then once you've put it in the hydrochloric acid and burnt off the hydrochloric acid and any contamination there is, then you place it in your sample and then you put the wire loop into a roaring blue flame and record the color that the flame goes. So you need to learn these flame colors. If you have sodium, the flame will go yellow. If you have potassium, it will go lilac. If you have copper, it will go a sort of a greeny blue. If you have lithium, it will go crimson red. And if you go calcium, you get this orange red, sometimes described as brick red. So sodium, yellow, potassium, lilac, copper, greeny blue, lithium, crimson red, calcium, orangey red. You just need to learn these. Learn the method. It's a nice simple method. Clean the wire loop in hydrochloric acid and put it in a Bunsen flame. Put it into your sample and then place it back into a roaring blue flame and record the color of the flame. And if that flame goes yellow, then it's sodium. If it goes lilac, then it's potassium. And it's as simple as that. Another test we can use for metal cations is the precipitate tests. Now, a precipitate is when you add two aqueous solutions together and get a solid product. So two soluble reagents react to form an insoluble product. So it's nice and simple. All you do is you take your substance, your aqueous metal compound, and you add sodium hydroxide, and you end up with a metal hydroxide being formed, and these are going to be insoluble. So that's all you have to do. You add a few drops of sodium hydroxide, and if you have aluminium, then you get a white precipitate. If you have calcium, you get a white precipitate, and if you have magnesium, you get a white precipitate. And this isn't by chance. If we think back to topic 1, when we were talking about the transition metals, one of the things that was unique about the transition metals is they formed colored compounds. So the reason aluminium, calcium and magnesium all form white precipitates is because they're not transition elements. Only transition elements form colored compounds. So any metal that's not a transition metal would form a white precipitate. So aluminium, calcium, magnesium, you just got to look at those and think, right, they're not transition metals, it's going to be a white precipitate. Copper is a transition metal and forms a blue precipitate. And then you've got two different ions of iron. You've got iron 2+ and iron 3+. And again, that's one of the things that you have to remember from topic 1. When we talk about the transition metals, they can have multiple different charged ions. So different charged ions form different compounds and have different colors. So iron 2+ would form a green precipitate, whereas iron 3+ forms an orange-brown precipitate, much like the color of rust. So if it's not a transition metal, it's going to form a white precipitate. Copper is blue, iron 2+ is green, iron 3+ is orangey brown. You just have to learn and remember these. The only other thing you need to remember is you can identify aluminium, you can separate aluminium from calcium or magnesium, because if you keep adding that sodium hydroxide, the aluminium precipitate will redissolve. So if I added some sodium hydroxide to a compound containing aluminium ions, I would get a white precipitate, but if I kept adding that sodium hydroxide, it would eventually redissolve. So you can identify aluminium from the other two by adding excess sodium hydroxide and seeing if it redissolves. If it doesn't redissolve, then you know it's calcium or magnesium. But that's everything you need to know about the precipitate tests. So here are the reactions that are actually occurring. So we've got our aqueous metal ions, and they're reacting with the sodium hydroxide. Now these are just the ionic equations. I've removed the sodium ions because they're just spectator ions. They're not doing anything worthwhile in the reaction. So the aluminium reacts with the hydroxide to form aluminium hydroxide. That's a white precipitate. The calcium ions react with the hydroxides to form calcium hydroxide, which is a white precipitate. The magnesium and the hydroxide form magnesium hydroxide, which is a white precipitate. The iron 2+ and the hydroxides form iron hydroxide, which is a green precipitate, and iron 3+ and our hydroxides form iron hydroxide, with a slightly different formula because it's got a different charged ion, but this one will be an orangey brown precipitate. So those were the two tests for the metal cations. Now we need to look at a variety of different anions, the negative ion in our compound. And the first one is the halides, okay, which is just the halogens but in their ionic form. So chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide. Once they've become an ion, they're now halides rather than halogens. Now the test for this is to add silver nitrate. Silver nitrate is the reagent for identifying the halogens. It needs to be acidified, silver nitrate, and because it's silver nitrate, we use nitric acid to acidify it. So you add your silver nitrate to your compounds, and if you get a white precipitate, it tells you it's a chloride. If you get a cream precipitate, that tells you it's a bromide, and if you get a yellow precipitate, that tells you it's an iodide. Again, learn and remember these. You need to know the reagents, the conditions, so which acid do you need to acidify it with. The reagent is silver nitrate, and if it's a chloride, white precipitate, bromide, cream precipitate, iodide, yellow precipitate. And again, the reactions, I've again gone for the ionic equations. So if you have a chloride, it will combine with the silver ions to form silver chloride, which is a white insoluble solid. The bromide combines with the silver to form silver bromide, which again is a cream insoluble solid. The aqueous iodide combines with the aqueous silver to form silver iodide, which again is a yellow insoluble solid. We also need to be able to identify sulfates, which is the SO4 2- ion. So this time, the reagent is barium chloride. And we acidify it again, but because it's barium chloride, we acidify it with hydrochloric acid. And if a sulfate is present, we get a white precipitate of barium sulfate. Now you don't have to use barium chloride. You could use barium nitrate. You'd get the same result. Only you'd have to use nitric acid because barium nitrate needs nitric acid to acidify it. Either way, if a sulfate is present, you get barium sulfate produced, which is a white precipitate. And here's the reaction for that. Again, ionic equation. So we've got our aqueous sulfate ion combines with our aqueous barium ion to form a white insoluble solid of barium sulfate. And finally, we have the carbonate anion, CO3 2-. So this is a nice simple test. You add a few drops of acid to your sample, any acid, doesn't matter which, any acid will do, and you observe to see if there's any fizzing. Is there a gas being produced? If you bubble that gas through lime water and it goes cloudy, then you have a carbonate. It's as simple as that. So you add an acid, because we should know that metal carbonate plus acid gives us salt, water and carbon dioxide. So we add our acid, we bubble that gas through lime water, and if that gas is carbon dioxide, the lime water turns cloudy, which confirms that it is a carbonate present. So here are the basically two reactions here. Here is our carbonate. The top one is the carbonate reacting with the acid. So we've got the H+, the protons from the acid reacting with our CO3 2-, our carbonate ion, producing water and carbon dioxide. And then we've got our carbon dioxide reacting with our lime water, the calcium hydroxide, to form that insoluble precipitate of calcium carbonate, which again is why the lime water turns cloudy. So finally, what we need to talk about is flame emission spectroscopy. So going back to the flame tests, there are a few limitations of the flame test. Number one, you can't identify mixtures. If you have a mixture of two different metals, well, you'd see both colors in the flame at the same time, and you wouldn't be able to distinguish between them. Secondly, if you've got two ions that have similar colors, for example, calcium and lithium, just different shades of red, that's quite difficult to judge just by visually looking at the flame. So flame emission spectroscopy is an analytical technique carried out in laboratories that measures the specific wavelengths of light emitted when ions are placed in a flame. So this allows you to compare the wavelengths emitted from the sample, and you can compare that to the wavelengths emitted from known reference samples. So if you had an unknown mixture and it gave you a particular wavelength of light, you could compare that to the known wavelengths given off by different ions and then mix and match and say, well, actually that matches this, so it must be, for example, lithium. It's much more expensive, but it does have a number of advantages. It is much faster. It is more sensitive, it's more accurate, it can identify mixtures of ions. It also uses a much smaller amount of your sample. So if you were perhaps a crime scene investigation and you only have a very tiny amount of the substance, you want to preserve it, don't you? You don't want to use it all up running tests just in case you need it for something else later. So the fact that this uses a very small amount of the sample is actually quite a big bonus. So in terms of what you're going to be expected to do, you're probably going to be given a spectra for a mixture, some known references to compare it to, and be asked to identify the compounds or the ions present. So if we have a look here, we have on the bottom left the spectra of a mixture. So a mixture has gone through the flame emission spectroscopy and has produced this spectra of different wavelengths of light. And above it we have the known spectra for calcium 2+, copper 2+, potassium+, lithium+, and sodium+. And all you've got to do is match them to see which ones are or are not in our mixture. So we're going to do this one by one. Let's look at calcium. And straight away I can see that loads of these wavelengths are not present in my mixture. I mean, there's no point looking at the ones that are, because there's very clearly ones that aren't. So we can immediately say it's not that one. We look at the copper, and straight away we should see that there are bands on the copper spectrum that do not appear in our mixture. And you just get a ruler and just follow them down. And if they don't match up, then it's not in there. So the copper is not in there either. The potassium, and again, I'm looking at this sort of really concentrated grouping of them in the middle. Look for the really distinct peaks. The 2 right on the end. That is not in our mixture, so it does not contain potassium. We'll look at the lithium. Well, actually, if you follow every one of those bands from lithium, you will find a corresponding band in our mixture. So I would say yes, it does contain lithium. And finally, sodium, again, look at those bands, they match up perfectly. So what we could say is that this mixture must contain lithium ions and sodium ions. So there will be some exam questions that I've put into an online form. If you could just use complete your worksheet and then use that to help you answer the questions.